Welcome back to Fusion24, welcome back. And if you're just joining us online, a welcome back too. Don't worry if you've missed any talks, they'll be available to watch on YouTube, complete with slides in a couple of weeks' time. Just check your email for details. In the session we just heard, you saw a huge variety of technical approaches to fusion. And one of the questions I'm often asked is, which one is going to win out? Which one should we back? Here to make the case for that diversity of approaches, please welcome onto stage physicist and fusion economist Niek Cardozo from Eindhoven University of Technology. Niek.
Yes, thank you so much, Valerie, and good morning to you all. There's been a lot of talk this morning about, maybe I should start pushing buttons. Yeah, okay, there we are. There's been a lot of talk this morning already about the famous 40 trillion valuation. So, by Bloomberg, I thought maybe that's a good starting point for this conversation. Now, 40 trillion, mostly it makes an impression because it's a large amount of money. But in real terms, it also means something else. It means, I mean, for me, it's just a posh way of saying that fusion is meant to take up a serious fraction of the energy demand in the world. Okay, so let's say 20 or 30% or so. Yeah. Is that a lot? Well, let's have a look at the websites of companies or organizations that work in fusion. And they typically, they exhaust the English language for different words of expressing the wonderful prospects of fusion. So this says virtually limitless, clean. Here, sure about the limitless potential, unlimited power. So some things that should stick out is that we expect it to be limitless. Now, here's a question to you. If you have limitless energy, what is the point of it if you're not using it? If we were to provide only 1% of the energy demand in the world, coal would be fine. It's also limitless, and it's not very dirty at that level. Okay. So, but what does it mean? Well, to provide 20 or 30% of the energy in the world, you need about 10,000 fusion power plants at a unit of about a gigawatt thermal. At 10,000 fusion power plants. Okay, I'm not the only one saying that. Here's Bob Mumgaard of CFS, who in the video that's on their website says, imagine 2050, we've got 10,000 fusion power plants providing 20% of the world energy. Wouldn't that be wonderful, he says. Okay, so what does it mean? It means that foremost, well, first we have to make something that works, but when we have different options, scalability of making them is going to be the key factor. Scalability, it means scalability of materials, it means we have to scale up the workforce. Now, scalability, okay, but we really have the responsibility to look down the supply chains and look what it really means. So there are ethical and environmental concerns. For instance, we know that, and it's often said, so fusion is limitless because it uses very little fuel. The fuel of a fusion power plant would be lithium. Forget about the deuterium, there's plenty of that, but lithium. But it only uses 100 kilograms per year per reactor, so virtually nothing. However, in order to make that happen, you need about 100 tons of the stuff to fill the blanket. And it's not just lithium, it's actually lithium-6. So you need about 10 times more of the lithium to fill the blanket. So now it's not so little anymore. But then, lithium-6 needs to be separated out from natural lithium. And that is a dirty process, which we don't have. And if you look at the materials used in that process, they're exclusively mined in China. So, scalability, if you want to build one fusion power plant, everything is fine, it's clean, it's not difficult. If you think, oh, but we have to do 10,000, scalability starts to be a real serious issue. Not saying those issues cannot be solved, but I'm saying a small issue times 10,000 is a big issue. Now, 10,000 fusion power plants, you say, I mean, what's the guy worrying about? We don't even have one. So, what kind of industry do you need? Well, this is very simple to work out. If you need to sustain 10,000 fusion power plants, and they have a 50-year lifetime, you need to build 200 per year. 200 fusion power plants per year. Today, we can't even build one per year. So that is a serious scale-up. For comparison, the fission industry builds 5 to 10 fission power plants per year. And they run about 430. And their workforce is about 2 million people, or millions actually. So it's not rocket science to work out that the industry we are looking at, that we need to build up, would be a workforce of maybe 100 million people or so. And it would turn over, if these things cost a couple of billions each, would turn over trillions. So this is where you see the valuation of the 40 trillion come into play. Now, it takes time to grow such an industry. We don't have it. We don't have it at all. How fast does that go? Well, typically, to grow a new industry, for energy at least, this is very well documented. First, you go through an exponential growth phase. So here's a picture that shows that. This is for fission, wind, and PV, wind onshore and offshore. And you'll see that, so this is a log plot, so the factors 10 on the vertical axis, and there's years on the horizontal axis, going all the way from 1960 to 2100. And you see that a doubling time of 3 years is typically what we have seen for fission, wind, onshore and offshore, in their growth towards, well, where they are now. Then they roll over at some point. This was very well documented in a Nature paper by Martin Haig and Gert-Jan Kramer in 2009, which happens at about 1% of the world energy demand. But let's just focus at the exponential growth for a minute. What does it mean for fusion? Let me make that very concrete for you. Well, first of all, the Eurofusion demo is planned somewhere in 2060. Well, that clearly is very late. And this is one of the reasons why so many private companies have said, well, we must be able to do that much quicker. So there we go, fusion, the private initiatives. And because we're here, I also put the STEP device in there. So there you gain some 30 years compared to the original schedules of ITRA demo. But of course, you still have to go through this growth curve, let's say with a doubling of a factor of 2 every 3 years. That corresponds to a factor of 10 every 10 years. Yeah, so 10,000 fusion power plants, exponential growth. Suppose, let's be optimistic and say that a number of the startups will be successful, and a number of the government plans that are very much sped up now in the UK, in the US, in China, Japan, are successful. So maybe we can have 10 initial fusion power plants, demonstration fusion power plants in 2040. Okay. And we go through that curve, then we would have 100 in 2050 and 1,000 in 2060. And by that time, the industry is so big that we could build about 200 per year, which means 1,000 every 5 years. So it still takes 50 years to get to that 10,000. But by that time, every year, you would see the impact of fusion growing. Yeah, okay, so that's the long-term perspective. What does it mean today? Well, I'd say 2 things. First of all, it means we are starting in a learning curve. Rights law would say there's the same amount of learning, the same factor of cost reduction, if you want, with every factor 10 in accumulated production. Okay. So what does it mean now? It means that if there's exponential growth and then linear growth, almost all of the learning has to happen during the exponential growth. So what do we need to do? We have to maximize learning in this phase, because later is too late. If you want to learn in the linear phase, well, first of all, it's going to take 50 years, and moreover, it's going to be very expensive. Secondly, if you're going to build 10,000 plants, the first 100 or so are going to be irrelevant for energy production. Just like the wind parks and solar panels that were put up in the 1990s are irrelevant for energy production. However, these are essential, have been essential, and are essential for learning. So the first 100 or so you just built to learn how to build better ones. Well, let's hang on to that thought and say, this is our mantra then. We have to plan for learning. We have to set up ourselves in such a way that we get the maximum learning. That means avoid early technology lock-in. Okay, but how do you do that? Well, the learning rate, how fast you learn, depends on two things. If you're building fusion power plants, generation by generation, first 10, then 100, then 1,000, the time between those generations matters. It's like the clock of the evolution. If that takes a very long time, no matter how much you learn during one generation, you're still going to learn slowly. But if that time is very short, you may not have enough time to learn. So then you're limited by how much you can learn within a generation. So how do you optimize this process? Well, first of all, it's really essential that building a fusion power plant doesn't take 30 years. It has to take a couple of years at most. Because then you have time to run it, learn, before you launch the next generation 10 years after the previous one. And then you have to maximize how much you learn during that one generation. And here's where the parallelization comes in. So you can only learn so much from a single concept. So if you want to learn faster, you don't want to do it in a linear fashion. You have to do everything that's vaguely reasonable at the same time. Yeah. And now you'll say, okay, but that costs money. Isn't it too expensive? Well, if you have a science program, like you build an accelerator, you run it, and you plan to build the next one 50 years later, but again, it's only one. But here, it's very different. Here, you plan to build one, and then you want to build a new energy infrastructure, something that will actually create value for society, also something that will actually create money for their investors. So value is the central concept that comes into the story now. So if you think about value, you think about how does the future value that we may expect to create set off against the cost of the de-risking, the parallelization, if you like, and the acceleration. And as you'll agree with me, in the first plot you'll see the cost of de-risking on the horizontal side. So how much money do you put in various concept trials? So the red line is just 1 is 1. And then there's the value that you expect to create. Well, if you de-risk, you increase your future value, but there's a limit to it. Inevitably, it's going to be a curve that goes up and then it rolls over, like the value curve I draw. And that means that there's an optimum. It's an optimization process. And that optimum is not at 0, it's somewhere, well, I'll show you in a minute. And of course, if you expect less value, then you can spend less money on de-risking. But basically, as soon as you think, well, this is going to work someday, and then it will be important, it is worthwhile to spend significant money on de-risking. And likewise, if you run a project, you say, okay, there's a cost of the project. If you stretch it out too long, it will become more expensive. But if you want to accelerate it, yeah, at some point you also have to spend more money. For instance, to ask companies to have parallel lines, to run your team in night shifts. But there too, it's an optimization problem. Yes, so, and the optimum is not at the lowest cost. You actually can spend money on acceleration. And if you expect a greater return, you can spend more money on acceleration. And why is that? I didn't explain the curve for the value, but value in the future is worth less if it's further away because of the discounting. And the discounting is because the investor could have put their money somewhere else and generate an income. And there's risk associated with things that happen in the future. Okay, so anything that can bring your income forward will help you, will increase the value, and therefore there's more money available in a sense to speed up your projects. Sam Ward and myself put this into formulas. You can actually make a little model, pen and paper for it. So there's the value, is the curve that I described. Here's the cost of the number of parallel concepts that you're trying, and there's an optimum. And it's quite a robust result that you need to try 5 to 10, better err on the high side, let's say 10 concepts in parallel to maximize your return, your expected return. Trying to pick the winner really is the worst possible strategy. If you think about future value, so value-led rather than science-led, try all the concepts that are on the table. If you want to read about it, you can find it here. So here's my take-home message. The minute an expectation of future value comes into the story, there you can calculate how much money you can spend on de-risking by parallelization. And you can do 5 or 10, maybe even more concepts at the same time. It's absolutely worth the money. And it's also very important to speed up the process, because the sooner we have it, the more it's worth for society and for the investors. So shorten the build time and really do everything you can to shorten that innovation cycle. That includes licensing procedures, etc. We really can't have fusion power plants that take 10 years to build. It needs to be much faster, or we will not learn fast enough. That's my message for today. Thank you very much for your attention.
Thank you, Niek, for your valuable insights and perspectives. Niek will be joining me back on stage later for questions, sure. So save your questions till then. But I'd like to continue on the theme of what we can learn from other industries and welcome onto stage wind pioneer Andrew Garrad. Andrew is a pioneer of the wind industry, it's fair to say. Earlier this year, he was awarded the Queen Elizabeth Prize for Engineering, along with your old collaborator, Hendrik Stiesdal. And both of them received it for their achievements in advancing the design, manufacture and deployment of high-performance wind turbines. Andrew's been working in the wind industry for 40 years and founded the consultancy Garrad Hassan, which is the technical, creative and commercial brains behind the first billion-dollar wind farm. Andrew, I think it's fair to say there isn't a wind turbine in the world that hasn't benefited from your work. And a question, I think, the big question I really want to ask you is, what can Fusion learn from wind? It's a big question, so I think perhaps we should just, break that down. But I think, first of all, could you just remind us, how much does wind contribute to the world's energy today?
Yeah, we'll answer that question in a minute, but I'll just react to your first point. My exposure to fusion has been about 50 minutes. So it's quite a big ask to tell me what you can learn. Yeah, so roughly speaking, wind energy produces about 7% of the world's electricity. In the UK, last year, it was about 30% of the UK electricity came from the wind, about 39% came from renewables. You asked me also how much yesterday, and I wish we'd had this meeting in December rather than June, because June is the least windy month of the year. Yesterday it was about 9%, last Sunday it was about 20%. Taken over the year, it's about 30%.
And this is why we need fusion to, just to work with renewables.
We don't just need fusion, we need everything.
Absolutely.
It isn't a competition. This isn't a competition.
No, I completely
This is a collaboration.
And recently, the wind industry sort of celebrated a remarkable milestone worldwide.
Yeah, a terawatt of installed electricity, of installed wind power. And that took about 30 years, I guess, to get from almost nothing to a terawatt last year. And I'm hoping that the next terawatt will be less than 10 years. It's quite interesting for me because we heard about, I think, from the American speaker this morning, she talked about 50 terawatts for a nanosecond. So these prefixes are different to mine. And I've always rather objected to billions, because I think if you talk about $1 billion, you really should say 1,000 million, because you remember how many that is. And now we're talking about trillions. So your prefixes are different to mine, and I think that's something we might return to.
So we've seen this remarkable progress in wind energy over the past 40 years. What has driven that growth? Is it the technology? Is it the engineering? Is it regulations and government support?
Well, it's a bit of everything, and I think it's a chicken and egg, really. I think if we go back to the 19th century, there were probably 5,000 wind turbines in Britain. There were water pumping or corn grinding, and similarly in other northern European countries. So and if we go back even further, 2,000 years ago there were wind well, they weren't called wind turbines, but windmills in Persia. So rather, I was trying to think earlier this morning what the differences were. So a big difference is we've had wind for millennia, and then there have been various important steps, I think. There was, during and just after the Second World War, there was quite a resurgence in looking at wind, or creating the modern era of wind turbines for making electricity rather than mechanical power. Actually, interestingly, in Denmark and in Germany and in the States and in the Soviet Union, it was quite a big effort in the Soviet Union, interestingly. Then oil became cheaper and that all died away. And then I think you can trace the latest generations of wind turbines back to the so-called first oil crisis, which hit Denmark particularly badly because they had no real substantial oil and gas. And so they took a very brave initiative to really push the wind energy business. And then we had a really fascinating event, or series of events. The northern German people in northern Germany and in Denmark were really building wind turbines literally in their backyards. I had some meetings in the late 80s, literally sitting on a bale in a farmyard with a guy making a windmill next door. At the same time, there was an initiative, big government money was being spent, well, big in our terms, by Americans and Europeans, giving money actually mostly to the aerospace companies, because these things looked a bit like aeroplanes. So people thought, well, if it's going to be developed, it's probably going to be aerospace. So there was big money being spent by GE, Hamilton Standard, Boeing, British Aerospace, Air Italia, MAN, MBB. And these two routes continued separately. So the small guys literally in the backyards and the farmyards, and the big guys, so there was science and practical development. And these, for probably about 15 years, remained almost out of touch with one another. And then there was a European Union or Commission initiative to bring them together, and that was called WEGA, Wind Energy Großanlage, a big windmill, literally in German. And that then kindled the beginning of the modern era, and it's gone on from there. So we can go back 2,000 years, or we can go back to the 50s, or we can go back to the 80s.
But similarly, if you go back to the 80s, we heard about a diversity of approaches to fusion. There was a diversity with wind turbines as well, wasn't there?
Oh yes, there certainly was. I mean, yes. I have a slide that I sometimes use, which is, it says, wind turbines 30 years ago, and there's everything. I mean, there are vertical, so the present ones we have that go around like that are called horizontal axis. There are also ones that go around like that, which are called vertical axis. There were, well, actually, I mentioned MBB. So MBB was given, so Messerschmitt was given some money by the German government to develop a wind turbine. They looked at it and they thought, oh, yeah, that looks like a wing. So that'll have to be carbon fiber. So that'll be expensive. So we better just have one. So the Messerschmitt prototype had one blade as a result of the aerospace thinking. So there were 1 blades, 2 blades, 3 blades, upwind, downwind, vertical axis, horizontal axis. There was everything. Now, if you see a windmill, you think there's a consensus, which is three blades, variable speed. If you look inside the nacelle, which is the machinery on top of the tower, there's lots of differences. The reason why we have 3-bladed turbines now is partly engineering, but it's also having to be a good neighbor, because people don't like 2-bladed, or well, 1-bladed is probably a very minority interest, but 2-bladers, when they go past the tower, they seem to stop. So you have this funny jerking sensation. Perfectly good from an engineering point of view, and actually perhaps even cheaper than the 3-blader, but people just can't live next to them. So being a good neighbor has been part of the evolution of the turbine designs. But yeah, they all look pretty similar now. As we go offshore, then of course the good neighbor constraint becomes rather different and it is relieved. Then it becomes a sort of engineering dream, because you're relieved of all the external pressures from the human neighbors. Maybe you have some other neighbors you have to worry about, but the engineering constraints are quite different offshore. So we may, as the offshore business matures, we may see different turbines developing. So you asked me, is it engineering or is it politics? We needed the politics. What we've demonstrated, I think, is that engineers will rise to the challenge. We're perhaps not very good as engineers in articulating the challenge, but we will rise to the challenge. And the challenge has been there, and it's needed a consistent policy from national or European governments. And the biggest single thing, the reason why we have so many wind turbines in Europe now, is that there was an initiative called the 2020 vision, which was 20% of our energy from renewables by 2020. And that was, we were all told that if we didn't do it, we'd be punished. And we all did do it. And that single initiative, a directive, European directive, I think has been absolutely key in developing the European industry and the European market. Chinese, we can maybe talk Chinese a little bit later on, but that's rather a different initiative, but also very successful.
Well, I mean, you mentioned China there. So what is the situation in China? Because, you know, we hear that they're still rolling out coal power plants, but also they're very big in renewable energy as well.
They're very big in everything, aren't they?
Everything.
I don't know, are they big in fusion?
Well, I think you.
You'll tell me later on.
We saw the remarkable video from the East machine in China, which
yes.
You know, the ambitions there do look incredible.
Well, you're right. They are producing still building coal power stations, but they do have a very clear mission for decarbonisation. When I first got involved in China, I went to China in the very early days when actually there were no wind turbines and also no cars. It's a pity they didn't keep the second. Beijing is now one huge traffic jam. They now have roughly half the world market. So half the installed capacity is in China, half outside. The 3 Chinese companies are the 3 biggest manufacturers, the 3 top Chinese companies are the 3 biggest manufacturers, and the 2 of them are making the 2 biggest turbines in the world. So there is now quite a lot of tension, I have to say, between the East and the West. And I think what the Chinese do in terms of development will be very important in determining what happens in the West as well. When I mentioned I was first involved, the guy, Wu Gang, who's presently the chairman and CTO of Goldwind, came to buy some software from us in Bristol. And he stayed in a youth hostel because he couldn't afford a hotel and shared a room with 5 other people. I went to see him just before Christmas last year, and he took me around his Beijing campus where he was making the world's biggest turbine and he employed 10,000 people. So you can see that's partly a signature of what happens in China, partly a signature of what's happening in the wind business. It's extraordinary.
And when we talk about world's biggest turbine, just tell me about how the size of blades has changed as well.
Well, when I started, I could carry a commercial wind turbine blade on my back, and now it's probably 60 tons. And the biggest one, which is actually just commissioned last week, is 287 meters in diameter. You know, it's very easy to say that, and it's easy to draw it on a bit of paper. But if you see one, you think, why? Well, expletive of some sort. Yeah, and even me, and I've spent my life, and I think, do we really want to do this? It is just, well, by far the world's biggest rotating machines, I mean, by far. And they are absolutely huge, and gobsmackingly huge. So our industry has been characterized by getting bigger and bigger and bigger. And there are now some questions being asked by everybody, I think, is, do we really want to go any bigger? And just as a slight tangent, something that's occurred to me recently, which I think is quite interesting, you have the two leading renewables of solar, or PV, and wind. And for me, the PV is sort of like black magic. You know, to make proper electricity, you need big rotating machinery. Everybody knows that. And somehow this magic stuff, you shine the light on it, it produces electricity. Well, you can scarcely imagine two more different bits of engineering than making lots of solar panels this size of that screen there, millions of them, all making a 287-meter diameter turbine. And yet, the cost of these two sources of renewable electricity seem to be converging. So I think there might be some sort of universal law of physics that electricity from renewables is this cost. And it's remarkable to see these two things coming together.
Yeah. So just as we're sort of in our final minute, coming back to that, advice for the fusion industry, if there was one piece of advice you would give to the people in the room here, what would that be?
Well, I'd be very patronising to give you any advice, but if I can tell you why I think we have been successful is because of a purity of purpose and a conviction that there is a solution. Now, when we started, certainly I was thoroughly patronised, and I was told that when I grew up, I would realise that you could only make electricity by splitting, or in your case, I suppose, fusing the atom, or burning coal. But we had, our little group of people had a real determination that there would be a solution, and we would make it. And I think, and I suspect it's rather similar here. I had in the end, 1,000 people consulting company working for me, and when I look back on that, they were extraordinarily driven and capable people, and I'm sure that was because of the purity of purpose. And I suspect that is a very similar thing in this industry.
Yeah, absolutely. Andrew, I literally could talk to you all day. I hope you'll stay and enjoy the rest of the day and discover more about fusion. One thing I will correct you on,
yes.
Fusion is the process that powers the stars.
Yes.
The sun has been with us for 5 billion years. So
yeah, and it's the sun that drives the wind as well. So the wind is driven by fusion, basically.
Precisely.
Okay, that's got that clear. That's good.
So, thank you very much, Andrew. I'd now like to welcome Niek onto the stage. I have left my iPad behind with the questions from the audience. Let me just get that. So, get your questions ready for Niek and Andrew. If you're watching online, get ready to type in the little chat box, and of course feel free to ask questions of each other as well. Do you have any questions in the room for either Andrew or Niek? Yes, you didn't get to ask a question earlier on. I'm sorry about that.
Hi, good morning. Very stimulating and insightful talks. Couple of questions, Professor Cardozo. If you look at the Apollo or the Manhattan Project and compare value-led versus science-led, I was just wondering about is there a need to concentrate energies towards certain solutions, or with regard to the diversity of approaches? So I was just wondering about historically, how do you compare that with regard to the outcomes as well?
I'd say the Manhattan project, of course, they also tried different approaches at the same time, and also on a smaller level, the sub-technologies tried everything they could think of at the same time. And I think that, so if you're pressed for time, and in their case, the value, which is differently defined, of course, but clearly there was a big value in getting there earlier, then that's what you have to do. And yes, for fusion, I think similarly, well, you have to estimate the future value, because within the fusion community, often we say like, well, we're going to save the world, and that's, you know, invaluable. But in the end, you're just going to build so many power plants that are going to create a cash flow that is only so much, because you sell the energy for a certain price. So you can actually calculate that, and then you can work out how many different things you can do at the same time. It turns out to be about 10. Yeah.
Hi. Question is about, you know, the exponential growth curves you showed, and what sort of tips that off, right? So, is it technological, or is it a cost? I mean, so like we've heard EVs became capable when laptop battery manufacturing got to a certain cost, and that allowed you to drive up the curve and make it cheaper and cheaper and cheaper. So, as you think about like the catalyst for that, triggering that growth, how do we think about that? Do we need to get to a certain cost of fusion, or is it a thing people need to decide to do? Because to create economic growth, you need to have reinvestment, right? And it's got to have an economic case. So, how do you think about like triggering that? What usually causes that to start?
Well, the exponential growth you see in practically every industry. So it also holds for smartphones, for instance, or LED lamps, or and there's the sort of natural growth rate. So PV has been very fast at the doubling time of 2 years. Others typically have 3 years, and it's like, yeah, you have to build something, you have to evaluate it, and then you go to your next model. And this is roughly the time it takes. In the case of fusion, the particular challenge is indeed that you need to make a lot of investments up front, and your payback time is going to be long, as it is in any energy technology. So there has to be trust, but typically, I mean, your first generation and second generation fusion power plants, just like wind and solar, are not going to be competitive in the market compared to fossil, for instance. So there'll be government incentives to level the playing field. And that is what helps the... So very important is that policies in that matter are stable, that people, the investors, know what they can expect.
Andrew, how did sort of government subsidies, you don't like to call them subsidies, I know, how did that, tell us about that and wind, in relation to wind?
I think they were crucial. Right? They were subsidies to start with, but yes, incentives is I prefer. And certainly we had a lot of criticism at the beginning when electricity from wind was very expensive compared with conventionals. Although I think now we're moving away from it. I'm not sure the levelized cost of energy is the key. I think we probably need everything. But what happened was there were incentives put in place in most of the countries where there is presently activity. Sometimes it was tax credits in the States, other times it was feed-in tariffs here in Europe. And they were very effective. I mean, they were really, they did prove that a subsidy can be a good thing. And if we look particularly recently at offshore wind, when offshore wind in the UK started, the growth, the learning curve was the wrong way. I mean, things got steadily more expensive as you did more of them. And I take, it's very common to criticize politicians. And usually we're all harping on about how useless they are. But actually, in Britain, the governments of both complexions stuck with it and kept on incentivizing or subsidizing offshore wind, and then suddenly it collapsed. The cost collapsed as a result of technology and volume and experience. So I think it's a very clear example of how a subsidy can work. And the question is how long you go on with the subsidy. And they do deserve praise for sticking with it when otherwise they might have given up.
We have a question online from Tony Donny, and it's a question for you, Niek. So almost none of the private fusion companies that we've heard about are tackling the issue of neutron-tolerant materials. How does that affect the outcome of your model?
Yeah, I think indeed many of the companies and research programs, national research programs, are aiming to make one working demonstrator. And to make one working demonstrator, you don't need to have the final materials yet. And the demonstrator only needs to work for a couple of years to demonstrate what it needs to demonstrate. Now, so there's two approaches. One is where you say, okay, but since the first 100 or so are going to be demonstrators anyway, they're not so important for real energy production. Let's first make the demonstrator, and in the meantime we work on the materials, or maybe even the government programs work on the materials, because we don't have all to solve all the problems right away. There's more time for some. Decommissioning you can think about longer.
And this is really the value of a government program like STEP, isn't it? That STEP can solve. Or STEP is certainly going to tackle all of those problems. STEP will be looking at the materials, the fuel cycle, the maintenance, and the private fusion companies, they don't have to think about that at the beginning, at least, but they will eventually.
It's like if you plan on learning, you say, I'll build one, and then I will build the next. You don't have to solve all the problems in the first model. If you think like the government's programs with ITER and Demo did, like we build one of each and then they have to be perfect in there for that time, then you have to take on all those issues right away. But that is on an innovation cycle that takes 30 or 40 years rather than 5 or 10 years. So, yeah.
Well, can I just add a little comment about following on from your earlier question, is that I suspect this isn't applicable to the fusion industry, but what we found was the most powerful way of developing the technology was through a market subsidy rather than through a capital subsidy. So it's quite difficult to see the results of big chunks of money being given to manufacturers, where it's very easy to see the effect of in creating a market. But I think the nature of a wind turbine and a fusion plant is maybe significantly different in that respect, so that parallel may be completely irrelevant, but that's what happened to us.
I think there's certainly lots of issues that you talked about that people in the room will relate to very much. We've probably got time for one more question in the room. Yes.
It's a question about wind power. What is the levelized cost at the moment, and does that take into account when the wind doesn't blow?
Yes, I mean, the levelized cost, as you might expect, it varies depending on where you are. so the levelized cost here offshore is about, well, I don't know what units you use, but 50 or 60 pence a kilowatt hour. Sorry, 5 or 6 pence a kilowatt hour, 50 or 60 pounds a megawatt hour. And well, does it include? That's what you're paid, and so you are feeding into the system, and so you're part of the system. So there are various evaluations of the balancing costs, which actually turn out to be surprisingly small, and that depends, of course, on the system to which you're connecting. So that element it's a very contentious item, but it's probably 10% of the normal levelized cost without balancing, and of course it varies as the systems develop, as the fuel mix changes. It's all up for grabs now, I would say. One last point. Connections, grid connections, are the key thing for us now. I think we've demonstrated that the technology works. We have a pretty good idea of the resource. We're pretty good at short-term forecasting, so bidding into energy markets. But if there isn't a connection, it's no good at all. And that's what you see in China, quite big wind farms without a cable.
Yeah. Gosh, yes. Similarly, Fusion has concerns about will the grid be ready. I mean, we've reached the end of our time. Before we thank Andrew and Niek again, I'll just tell you what's going to happen after the break. On this stage, we will have a panel discussing the remarkable progress that's being made towards siting, designing and building power plants for different markets and what that could mean for you and your business. And down on level 2, we'll be looking at how artificial intelligence is being used in Fusion and the prospects for speeding up the design of power plants and cutting the costs. And so that should be starting off at about,
No.
Oh, yeah, probably. Yeah, we're running a bit behind. We'll let you know when that's about to start. So for now, please put your hands together and thank Niek and Andrew for their wonderful talks. Thank you.